Hello and welcome to this introductory video on transformers. In this video we're just going to take you through a simple transformer and show you some cool features that explain hopefully how this transformer works to step down voltage or increase voltage. So the basic idea of a very simple transformer is you start off with some potential V, which you use to create some current through some nice coil. Okay, and of course if you alter V, then you can create, well, if you send it through, you've got a magnetic field because you've got a current, say it's in that direction. If you change V, that changes the current, that will create a changing magnetic field, and we know that that changing magnetic field then could induce an EMF in some other, say, loop. Now the trick with a transformer is you also add a nice little core to the thing to guide your magnetic field over to the other loop. Okay, so we'll have another loop over here. So we'll call this our primary, which has a voltage primary and has a number of turns NP in its coil. I got a number of turns in the secondary, and we're going to generate or induce an EMF, which we will just describe as a potential of the secondary coil. Okay, so we use this, change the primary voltage, that's going to change the magnetic field going through here. This iron core translates the field along and through the secondary coil. So that then is also changing as a result of the change due to the primary coil experiencing this oscillatory potential, say. And so what's going to happen? Well, this magnetic field passes through there and it's changing. That changing flux through that second coil will induce a potential or an EMF across that secondary coil. That's the idea of the simple transformer. How does that help us actually change voltages and things like that? So if these coils are identical and you haven't really lost anything in guiding that magnetic field around, then you really haven't achieved anything except separated out the currents for no good reason. But if you change the number of turns, well, that has a very important effect, because recall that the EMF that you induce, so let's go ahead and swap. The EMF induced in the secondary is going to be the number of turns in the coil, delta phi delta t. Well, what is delta phi delta t through the second? Well, it's the same as delta phi delta t through the first. But what should that be equal to? Well, I could write that the EMF of the primary should be minus the number of turns of the primary, delta phi delta t, since it's the same change in flux. So I can rearrange. Delta phi delta t must be EMF in the primary divided by the number of turns in the primary. So I can write that the EMF in the secondary, which is that, is just, let's finish this statement. I can put that into the expression. I've got minus ns times minus EMF primary on the number of turns in the primary. Right. Okay, I can ditch the minus signs at that point. And so I'm just looking at the number of turns in the secondary. May as well write it that way. Number of turns in the secondary divided by the number of turns in the primary times the EMF of the primary. So by adjusting the number of turns in the secondary coil, I can either increase or decrease that potential. Right? And that's what transformers are for. So still rearranging that and replacing EMFs with V, this is the expression that we're looking at, or exactly the one that I've now rearranged to. If you have more turns in the secondary, then you are increasing the voltage, and if you have less, then you're decreasing the voltage. So this is exactly how transformers work. Some food for thought about transformers then. Given that the power that you're inputting must be the power that you're outputting, assuming that you haven't really lost much in going through that core, and knowing that the power must be equal to I times V, then you find an expression for the current in the secondary coil, just in terms of the current in the primary coil and the number of turns in each coil.